We've all seen the solar system pictures in textbooks. The Sun, slightly larger than Jupiter, but that isn't the right depiction of the scales. The Sun is so massive that you could fit about 1,000 Jupiters inside. Impressive as it is, our Sun isn't the biggest star in the universe or even our galaxy. That title goes to Ui Scott. Compared to it, our star is like a tiny pebble. But there's more. Scientists have stumbled upon something even more mind-boggling. An enigmatic ancient star with a black hole inside. It's an astronomical mystery that both puzzles scientists and can potentially explain how the universe came to be what it is today. But how is it possible for a black hole to exist inside a star? Why were these stars so gigantic? And what would happen if a black hole star wandered into the solar system? Stars are like cosmic blacksmiths. In their fiery cores, they're forging the majority of the elements we observe in the universe. But the stars that could have existed at the very beginning of the universe were something different. Instead of conventional stellar cores, they harbored black holes within, allowing them to grow to unimaginable sizes and beyond ordinary stars arise from clouds of gas and dust. As gravity makes the densest regions of the cloud collapse, the resulting mass of material heats up and creates a protostar, an early stage in the evolution of a star. Eventually, the newly formed hot core accumulates enough matter from the surrounding rotating disk of gas, becoming a main sequence star that starts producing energy through nuclear fusion. It took our Sun about 50 million years to reach this phase. The majority of stars will spend most of their lifespan as main sequence stars, but eventually they will all either become white dwarfs if their mass isn't big enough or go supernova. After a star blows up, it can end up as a black hole or a neutron star, and the path it takes depends on how massive it was. When our Sun runs out of hydrogen in about 5 billion years, it will turn into a red giant, expanding 200 times in size before finally shedding its outer layers and transforming into a white dwarf, a celestial object that's roughly 200,000 times denser than the Earth, but about the same size. This dense sphere will then slowly cool to about 18 million to 10 million to C, and in about 10 billion years the white dwarf Sun will crystallize. The process is somewhat similar to how water turns into ice, although the material is different. In the case of the Sun, it will be carbon and oxygen solidifying, and stars over 10 times the mass of the Sun will have a different fate. They're big enough for their cores to collapse after a supernova, but they lack the mass required to become black holes. So where does this leave them? Deep inside these stars, the extreme pressure squeezes every proton and electron so tightly they merge to form neutrons. Neutrons cannot be compressed any further, so they counter gravitational pressure, and the star finds a new balance. Neutron stars are the densest objects in the universe. Apart from black holes, they can be just the size of a small city, roughly 12 miles 20 kilometers, but still have a mass of the Sun on Earth. Neutron star material the size of a sugar cube would weigh as much as 1 billion tons, about as heavy as a mountain. But how do stars become black holes while the star is still active? The two prevailing forces work against each other: nuclear fusion and the intense gravity created by the star's own mass trying to squish it. Once there's no fuel left to power nuclear fusion, there's no longer a force to counter gravity, and the star collapses in on itself, just like the controlled demolition of a concrete building. Einstein believed that anything could become a black hole if it had sufficient mass and was compressed inside a certain radius. Black holes keep on growing throughout their lifespan, devouring any material that gets too close. When this happens, the region where gravitational pull becomes so strong that nothing can escape increases, and the black hole consumes even more nearby material. It's somewhat like the sinking of ground due to the collapse of underground structures. Although with black holes, it is a gravitational sinkhole gradually accelerating as its event horizon grows. Normally black holes have a limit on how fast they can expand. This happens because of something called the Eddington luminosity limit. Basically, it's the point at which a black hole can't take in material faster than it already does. If you were filling a car tire with air, and it had small holes in it, the increased pressure inside would make some of the excess air escape in space. Something similar happens with rotating black holes. As matter spirals toward a black hole, it goes faster and faster. Because of this, about 42% of this matter can be converted into energy, and this radiation is so powerful it can push some of that incoming material away, just like a car tire pushes the air away. This process is so efficient the radiation emitted away surpasses the energy output from nuclear fusion in stars. Just imagine a future where we find a way to harness this energy and use it for our needs. Even supermassive black holes with a large surface area that attracts matter have this limit. They are at the center of almost every galaxy out there, and some of these supermassive black holes have been recently discovered to be much larger than we thought. That's one of the greatest mysteries in astronomy. The gradual accumulation of matter over the age of the universe fails to explain their enormous size, but there's something that might unravel the mystery. Black hole stars, or quasi-stars, must have been the largest celestial bodies. to ever exist, dwarfing even the most gigantic black holes we've discovered so far today. The conditions of the universe do not allow black hole stars to form, but at the beginning of time, space was packed with massive gas clouds. Within these dense regions of space, material collapsed in on itself under its own gravity, and because there was so much more of it, it piled up, giving rise to baby stars of extraordinary magnitude, although there's an idea that they may have originated from dark matter. Halos, invisible spherical regions of dark matter of up to 100 million solar masses, where thousands of supermassive stars could form. Normally large stars would go supernova and leave behind massive black holes, but these celestial giants weren't just large, they were so huge their size allowed them to absorb the explosive force that would otherwise shoot the star's outer layers out into space. Instead, these ancient stars only experienced implosions which transformed their stellar cores into tiny black holes while keeping the outer layers intact. If you could somehow observe this phenomenon from a close distance, you wouldn't even notice any changes with the star. Now that there's a baby black hole inside a quasi-star, it starts eating it from the inside. At this point, the black hole is tiny, but it's spinning, and this creates a disk of hot material circling it at nearly the speed of light. On top of that, there's no longer a limit on how fast it can devour gas as the star's pressure sends it straight into the black hole. The friction within the accretion disk becomes hotter and hotter, emitting tons of radiation and making the host star glow like a small galaxy. Quasi-stars, if they existed, grew faster than any black hole we've ever observed. Eventually, within millions of years, some of them would beat the largest stars and black holes in size that we know about, like Stephenson 2 to 18 UI and T618. Just how large is that? From thousands of times larger than the Sun to potentially even the diameter of our solar system and beyond. But this gargantuan size and mass also causes problems. The larger quasi-stars become, the shorter their lifespan. Our Sun has been around for over 4 billion years, with approximately 6 billion years left in its lifespan, while black hole stars lasted for just a few million years before spectacularly exploding with unprecedented power, releasing an ever-hungry monstrous black hole, ready to drift across space in search of more material to gobble up. But what if a star like this wandered into our peaceful celestial neighborhood? Once a quasi-star found its way into the solar system, its gravitational influence would disrupt the established orbits of planets and celestial bodies. The once orderly planetary system would be in total chaos, with Earth experiencing a severe asteroid rain. The effects would start before the quasi-star entered our solar system completely. As the gigantic star swallows the outer planets and other celestial bodies, our planet would already experience a surge in temperature and luminosity, making the surface inhospitable, until finally it would consume the Earth too. Although life here would long be gone by then, the central black hole H within quasi-stars could have served as seeds for the formation of supermassive black holes that are at the centers of galaxies today, and they might have even played a bigger role. The dynamic processes associated with quasi-stars, such as the collapse of the central black hole and interaction with the surrounding matter, could be potent sources of gravitational waves, which in turn may have played a role in the formation of galactic structures and the distribution of stars within galaxies. But not just that, quasi-stars could have implications for astrobiology. The intense radiation from these objects might have affected the habitability of planets in their vicinity, potentially shaping the conditions for life in unexpected ways. That said, in the context of cosmic evolution, quasi-stars might have set the future by shaping the early universe in unthinkable ways. But here's another mind-blowing thought for you. Although there are probably no quasi-stars in our universe today, tiny black holes roughly the mass of an asteroid from the dawn of time might still be here. Theoretical physicists speculate that if such black holes were abundant, they could be drifting around space, sometimes ending up trapped within gas clouds there. As new stars would be born, primordial black holes would eventually find their way into the star's cores. Even black holes, the mass of Pluto, would grow enormously within just a few 100 million years, a relatively short period of time in a star's evolution. So even our Sun could have one, which the great late Stephen Hawking once suggested, if it hit a black hole about as massive as Mercury, we wouldn't even notice it, although it's very unlikely. But there's one method scientists think might help identify such cosmic containers for primordial black holes. For one, the so-called Hawking stars would be much more long-lasting, and to cool off, Hawking stars expand into red giants, something our Sun will do as it ages. But red giants with a tiny black hole inside would be a bit cooler than they normally are. Researchers have already detected about 500 abnormally cool red giant stars. To find out whether these stars hide primordial black holes within, scientists plan to observe the stars' unique vibrations as they pulsate, which could signify they indeed aren't ordinary red giants. One of the most intriguing aspects of black holes is their ability to defy conventional understanding of space and time. According to Einstein's theory of general relativity, black holes are regions where gravity is so intense that not even light can escape from them. This phenomenon occurs when a massive star collapses under its own gravity at the end of its life cycle. The core of the star undergoes a catastrophic collapse, forming an infinitely dense point known as a singularity surrounded by an event horizon, a boundary beyond which nothing can escape. Black holes come in various sizes, from stellar mass black holes, which are several times more massive than our Sun, to supermassive black holes, which reside at the centers of galaxies and can be millions or even billions of times more massive than the Sun. The discovery of gravitational waves in 2015 provided direct evidence of the merger of stellar mass black holes, confirming their existence and behavior predicted by Einstein over a century ago. Supermassive black holes, on the other hand, are thought to form through several mechanisms. One theory suggests they may grow from smaller black holes merging together over time. Another posits that they may form directly from the collapse of massive clouds of gas in the early universe. These behemoths play a crucial role in the evolution of galaxies, influencing the distribution of stars and the formation of structures we observe today. One of the key properties of black holes is their entropy, which is a measure of disorder or randomness in a system. Black holes have the highest entropy of any known object in the universe, despite their simple structure. This paradox has led to significant advancements in theoretical physics, particularly in understanding the relationship between gravity, quantum mechanics, and thermodynamics. Black holes also challenge our understanding of the fundamental laws of physics, particularly the concept of information preservation. According to classical physics, information about particles and their interactions should be conserved. However, black holes pose a conundrum known as the black hole information paradox. If information falls into a black hole and is lost, it would violate the principles of quantum mechanics. The resolution of this paradox is still an active area of research in theoretical physics. Recent advancements in observational astronomy have provided new insights into the behavior and environment of black holes. Techniques such as very long baseline interferometry, VLBI, and the Event Horizon Telescope, EHT, have enabled scientists to observe the immediate surroundings of supermassive black holes with unprecedented resolution. These observations have confirmed predictions of general relativity and shed light on the powerful jets of material ejected from the vicinity of black holes. The study of black holes extends beyond astrophysics to include philosophical and existential implications. Black holes represent the ultimate end states of matter in the universe, where physical laws as we understand them break down. They challenge our perception of space, time, and the limits of human knowledge. In recent years, researchers have also explored the possibility of harnessing black holes for practical purposes, such as energy generation. The intense gravitational forces near a rotating black hole could theoretically be used to extract vast amounts of energy, although the technological challenges involved are immense. Looking forward, black holes continue to captivate the imagination of scientists and the public alike. Future missions and observational campaigns, such as the Laser Interferometer Space Antenna, LISA, and the Next Generation telescopes, promise to further unravel the mysteries surrounding black holes and their role in shaping the cosmos. In conclusion, black holes remain one of the most enigmatic and fascinating objects in the universe. From their formation to their profound influence on galactic evolution, black holes challenge our understanding of fundamental physics while offering profound insights into the nature of space, time, and the universe itself. As technology advances and our observational capabilities improve, we can expect even more groundbreaking discoveries that will continue to reshape our understanding of these cosmic giants.